Hello everyone, I'm Thomas. Since its release, segment routing has attracted a lot of attention. So why are all eyes on segment routing right now? What benefits can it bring to customers? And how can it be implemented? These are the questions we're going to go over today. As we know, services are becoming more and more diverse, and different types of services naturally have different requirements on the network. If we still cling to traditional methods and continue to merely passively adjust the architecture and configuration of the entire network, then we can't meet the requirements of today's rapidly changing services, and we'll also find that networks become increasingly complex to deploy and difficult to maintain. The solution to this problem is moving from the previous model, where the network adapts to services, to the service-driven network model, where services define network architecture. Specifically, a model where the controller first collects network information and then calculates an explicit path based on the service requirements put forward by the application. This is the background behind the development of segment routing. Segment routing works by dividing the network into several small pieces and then distributing segment IDs to these segments and network nodes. Through arranging nodes by segment ID, we can obtain a complete forwarding path. To break it down even further, this process consists of 6 steps. The first step is configuring IGP. Links in the network are each allocated an SID in order to generate a link label. These labels are equivalent to the numbers given to highways linking cities. The second step is configuring SIDs for network prefixes and nodes in order to generate prefix tags and node labels. In the same metaphor, these are equivalent to city or area codes. The third step is advertising these generated SIDs to peers using IGP. Step 4 is to perform path calculation using IGP. For step 5, the path code calculated by the ingress node generates tagged path information. In the 6th and final step, the ingress node encapsulates path information into data packets according to the MPLS forwarding mechanism and performs hop-by-hop forwarding. So what are the advantages of segment routing? The first advantage is that it simplifies the MPLS control protocol. Let's take a quick look at MPLS-TE. First off, it's a connection-oriented technology. In order to maintain the current connection status, it must be able to handle a large number of update messages being sent between nodes. This process occupies a lot of CPU resources and network bandwidth. Additionally, the number of MPLS labels varies according to the number of LSPs. An increase in the latter leads to an increase in the former. Labels consume a lot of resources, which is not conducive to building a large-scale network. It is also worth noting that MPLS path adjustment is distributed. If a service changes, MPLS must adjust the configuration of every individual node. Let's get back to segment routing. For segment routing to control service paths, it needs only to perform label operations on packets at the ingress node. No such operations are required at any intermediate nodes. As a result, pressure at the control plane is minimal. Unlike MPLS, the number of segment routing labels is equal to the total number of connections and nodes. However, the number of segment routing labels is unrelated to the total number of tunnels. In segment routing, path adjustment is centralized. If its services change, segment routing only needs to adjust service configurations at the ingress node. The second advantage of segment routing is that it can better implement SDN. Because it is an extension of existing protocols, network evolution is more smooth and disruption-free. Additionally, it uses the source routing technology to control and adjust service paths through the ingress node, enabling the network to more quickly respond to the demands of upper-layer applications. On top of that, it provides a balance between centralized control and distributed control in order to prevent the controller from becoming a service bottleneck. The third advantage is that it provides high protection ratio FRR protection. The traditional LFA and RLFA technologies have topology constraints that mean they are unable to implement 100% fault protection. For example, let's say that B wants to forward data packets to F, but there has been a link failure between B and E. B first forwards the data packets to C. The link cost between C and D is 1,000. So C then forwards the data packets back to B, which forms a loop, causing a forwarding failure. The TI-LFA technology uses an explicit path to establish a backup path without topology constraints. In theory, it is able to achieve a 100% FRR protection. When using TI-LFA in this same example, where the link between B and E is faulty, B directly enables TI-LFA FRR backup entry and adds new path information to the data packets to ensure that the data packets can be forwarded along the backup path. In addition, TI-LFA FRR also supports anti-microloop switchover and switchback, enabling end-to-end FRR and simplifying O&M. In conclusion, segment routing is a tunnel technology that effectively replaces MPLS in their many shared application scenarios. Multiple common services that utilize MPLS tunnels, such as public network services, eVPN, L2 VPN, and L3 VPN, can be smoothly switched over to segment routing tunnels. Thank you everyone for joining me today.